Algebra 2, Chapter 16.1, Exercises 1 through 12. Express each expression as a single logarithm. Simplify if possible. We're going to use the rules or the properties from this table, and the primary being product property of logarithms, the quotient property of logarithms, the power property of logarithms, and change of base. Also, the log with whatever base of 1 is equal to 0, that's another property. The log, if the base is the same as the number being taken the logarithm of, then that is 1. And then that's all I'm going to highlight for now. So let's go ahead with these exercises. Okay, what we have is a sum of two separate logarithms, and these logarithms have each of them the same base 9. And so we're going to use this, first of all, this product property of logarithms. And so we're going to take this log base 9 of m plus log base 9 of n and create a single logarithm going in this direction. So what that's going to be is, that's going to be log base 9 of the product of 12 and 546.75. Okay, so, and then we're going to use next the change of base for that, and the change of base is going to be log of, and another thing I didn't mention is whenever we see log, that's going to be assumed to be log base 10. Whenever you see ln, that's assumed to be log base e, e being Euler's number, about 2.718 anyway. So we're going to take log of 12 times 546.75 over log of 9. So we go to our calculator, and here it is. Okay, what we have is log of 12 times 546.75 divided by log of 9. So we'll just use the product property and the change of base formula, and we get 4. So our simplified answer for this one is going to be 4. Okay, and this one here, problem 2, which I'm not going to do in this exercise set, what we're going to use for that one is the quotient property of logarithms, which is this one here. So and I'll just write that down. Log of m minus log of n equals log of the quotient of m over n. So that would be the rule used for number 2. Okay, number 3. We have log of base 2/5 of 0.0256. And so what we're going to do with this one first is take That's log base 2/5. And one thing you got to be careful about here is just making sure you write this in a subscript manner so it's apparent. So 0.0256 to the third power. And what we're going to use for this one is this power property. So we're going to take this exponent here, 3, and move it out front. So that's going to be equal to 3 times log base 2/5 of 0.0256. And really, what we can do is we can work this out as 3 times. We can use a change of base formula, log of 0.0256 over log of 2/5. So we can go to our calculator now, and in our calculator we can put 3 times log of 0, I'll just say point 0.0256 over log of 2/5. So I'll put log of 2 divided by 5, and that should give us our answer here, 12. Okay. Then you look at number 4. You take this 23 out front. That'll be quite similar to number 3, actually. Number 5, we have log base 5 of 5 to the power of x plus 1 equals log base 4 of 256 to the power of 2. I think this one can be worked out without the calculator. Now what we have is, I'm just going to rewrite this, log base 5 of 5 to the x plus 1 plus log base 4 of 256 to the power of 2. And so we have different bases of these logarithms, don't we? So let's see how that works out. Well, for this first one here, we can realize that the log of base 5 and 5 will cancel each other out to leave us with x plus 1. And a better way to articulate that might be take that power property of logarithms and move this out front. So this first logarithm here is going to be equal to x plus 1 times log base 5 of 5 plus log base 4. And we can write, if we can write 256 as a power of 2, that could be helpful to us here, or better yet, as a power of 4. Let's see, 4 times 4 equals 16. 16 times 4 equals 64. 64 times 4 equals 256. So what we have is 256 is going to be 256 equals 4 times 4, which is 16, times another 4, which is which is 64 times another 4, or 4 to the 4th power. So we can write this 256 as 4 to the 4th power, and we can bring this 2 over there. So we've replaced this 256 with this 4 to the 4th power. Okay, let's just continue here below. For this quantity x plus 1 times log base 5 of 5, well, log base 5 of 5 is going to be, what power do you raise 5 to equal 5? Well, that's 1. So this is going to simplify just to x plus 1. And now for the one on the right, we have plus log base 4. And when we have, using the exponent property, we can make this 8. So we're going to have 4 times 2 is 8. So we have 4 to the power of 8. So that's it. Next we can bring down x plus 1, plus this exponent of 8 can come out front. So we have plus 8 log base 4 of 4. Well, log base 4 of 4 is 1. So we're going to get x plus 1 plus 8, which is going to simplify to x plus 9. So that'll be our answer to number 5. Okay, and then I think with this one here, you can probably do similarly for number 6. Anyway, yeah, again, the log is log base 10. Next, number 7. We have log base x plus 1 of this expression here to the 3rd power. And so let's go ahead and see if we can simplify that. I'm just going to rewrite this here. Log base x plus 1 of quantity x squared plus 2x plus 1 to the 3rd power. Well, we can write this x squared plus 2x plus 1. That is going to be equal to quantity x plus 1, x plus 1, or quantity x plus 1 squared. Now, where did I get the idea for this? In part, I got the idea because I saw this base of a logarithm, and so it would really be convenient if this happened to be some kind of power of x plus 1. So I'm going to rewrite this here as log base x plus 1 of, I'm going to put x plus 1 squared, and then we raise that to the power of 3. And so what that leaves us with is log base x plus 1. And we're going to have x plus 1. And what is 2 times 3? Well, that's going to be 6. And now we can take that 6 out front. So we get 6 log base x plus 1 of x plus 1. So what power do you raise x plus 1 to equal x plus 1? It's going to be 1. So that's going to be equal to 6. And that is our answer to problem number 7. Okay. Next, let's go ahead to problem 9. And now we're getting to the real world problems. Some of these real world problems are going to be like exponential problems like we did back in chapter 13, but we can solve them using logarithms. So a seismologist used the Richter scale to express the energy or magnitude of an earthquake. The Richter scale magnitude of earthquake M is related to the energy released in ergs, E, shown by the formula. Here's our formula. In 1964, an earthquake centered at Prince William Sound, Alaska, registered a magnitude of 9.2 on the Richter scale. Find the energy released by the earthquake. That's one of the most powerful earthquakes in recent history. Okay, so let's go ahead and put these values in and simplify and solve for E as best we can. So M is the magnitude of the earthquake. So we're going to put 9.2 is equal to 2/3, and we're going to have log of the fraction, the quotient of E over 10 to the 11.8 power. So that's what's going to. So we're going to just go ahead and gradually solve for E, and then we'll have the energy released by the earthquake. So the first thing we're going to do is get rid of this 2/3 by multiplying by the reciprocal of 2/3, which is 3/2. And so when we multiply by 3/2, the 2/3 will be canceled out. And so we have 3/2 of, I'm just going to put here 3/2 of 9.2. Let's get the calculator. 3/2, which is 1/5, times 9.2. That's going to be equal to 13.8. So left side now we have 13.8 is equal to, now we can use the quotient property of logarithms. So we're going to have the log of E minus the log of 10 to the 11.8 power. Okay, so that's what that's going to be. And if we remember, we have log base 10. We have log base 10. So 13.8 is equal to log base 10 of E. And then what we have is we can take this minus this 11.8 power. We can take 11.8 out front, log base 10 of 10. Well, log base 10 of 10 is 1. So what we have left is 13.8 equals log of E, and we're going to have minus 11.8. And now if we add 11.8 to both sides of this equation, we are going to have, I'm going to bring this up here now. On the left side now, we're going to have 25.6 is equal to log of E. Okay, so what we can do now is we can make this 10 we can take the power, so we can put this is right exponential 10 to the power of 25.6 equals 10 to the power of log base 10 of e. And then what we're going to do is, what we have for this is the 10 and the log base 10 cancel each other. So what we have left is e, or we'll put 10 to the power of 25.6 is equal to e. And then we can write this as, if we want to, we could write it differently. That's going to be, this is the way the book has it, 10 to the 25th times 10 to the 6th power is equal to e. And, or it's going to be 10 to the 0.6 power. To the 0.6 power is equal to e. And to find out what that is, we can go to our calculator and put in 10 to the power of 0.6. So we get about 3.98. So our answer is going to be E is approximately equal to 3.98 times, that's a times 10 to the 25th power ergs, because that's our unit. So that is our answer for number 9. Okay. Again, for number 10, we have an astronomy problem where we have variables that we go ahead about solving for. Getting to number 11, the intensity of sound of a conversation ranges from 10 to the negative 10th watts per square meter to 10 to the negative 6th watts per square meter. What is the range and loudness in the conversation? And what unit we're looking for here is this one here, decibels. Decibels, that's what we're looking for. So range in decibels. And so in fact, it really doesn't give the equation here, but the equation for decibels, so sound intensity, I'm going to put dB, the decibel, or the amount of decibels is equal to 10 log I over I sub 0. Okay, in this case, we're given two situations. The decibels, we're going to take the first one here, 10 log, and we're going to take the lower range, 10 to the negative 10th power over 10 to the negative 12th power. And what this is going to be equal to is 10, we have as log, and 10 to the negative 10th power divided by 10 to the negative 12th power is going to be equal to 10. These negative 10 and 12 cancel out each other. So we're going to get 10 over 10 to the negative 2 power. Okay, because that will cancel this out. And actually it'll be 10 to the 0 over, so it's going to be 1 over 10 to the negative 2 power. It's going to be equal to 10 squared equals 100. Okay, so we'll just say 10 squared. And then we can multiply this 2 out front equals 20 log base 10 of 10, which equals 20. So 20 decibels is what this 10 to the negative 12th watts per square meter equates to. Next, we're going to try our next one. It's going to be 10, and we're given log. We're given 10 to the negative 6th watts per meter. So 10 to the negative 6 watts per meter over I sub 0, which is 10 to the negative 12th. And what this is going to be equal to is negative 6 minus negative 12 equals negative 6 plus 12 is equal to 6. So this is going to be equal to 10 log of 10 to the 6th power. And what that's going to be equal to is 6 times 10, or 60 log base 10 of 10, which is going to be equal to 60 decibels. So the sound ranges, the loudness ranges between 20 and 60 decibels. And 20 decibels is very soft talking, like a whisper, and 60 decibels is pretty loud talking, so that really is kind of an appropriate range of loudness. And then for problem 12, we have a situation of sound intensity, and it's going to use that same equation we used for problem 12. Decibels is going to be equal to 10 times the log of I, sound intensity, over I sub 0, and then I sub 0 equals 10 to the negative 12th watts per meter squared. So anyway, that's really going to be it. I hope this has been helpful to you. And as always, thanks for viewing.